Well, greetings, mathletes, and welcome back. We're going to continue our discussion of logarithms today. And what we're actually going to be focusing on are properties of logs. So basically, ways you can manipulate log expressions into other log expressions. The reason we're doing that is because we want to be able to solve equations. And oftentimes, you've seen before with equations, you have to kind of massage one side or manipulate it this way or that way to get to come to a solution. And so, what we're going to be doing here is learning all the ways we can manipulate logs so that we can solve equations afterwards. And one of the things we're going to find is that with solving equations, exponential functions are the key to solving equations with logs in them, and logs are the key to solving equations that have exponentials in them. So we're going to take a look. We're going to develop those properties. I'm actually going to do a hard proof on the first one, and then the other properties are just consequences of that. And then we'll just see how to use them. Because looking at what the rule is formally and looking at how it's used, oftentimes those two things feel like different things, just because it's used a little more loosely than the way it's presented as a rule in the first place. So in any case, let's go ahead and get started here. Oh, someone moved my whiteboard over. Who did that? Whoever's responsible for that is going to be punished. Okay, so properties of logarithms. Okay, good. I got my pen set and everything this time. And so I'm going to develop these. If I can, I'm going to keep a list of the properties as we discover them. But if I run out of room, I'm just going to have to summarize it at the end. So we'll see how it goes here. So the first property is the addition property, sometimes called the multiplication property, because it describes the relationship between addition and multiplication when you're talking about logs. So the addition property basically says that if I have a log base b of some value and I add it to a log of the same base of some other value, I can actually compute that as a single log, right? Log base b, so all three logs have the same base of the product of the two. One of the things I want you to remember as we go through these is that these equations go both directions. We have a tendency, because we read from left to right, to think that the equations go in that order too. Equations they're reversible sentences. They are sentences. They have a subject, they have a verb, and they have an object or a predicate, right? It's actually, for you English nerds out there, that's a predicate nominative. But it's stating it in a sentence. This sentence is reversible. I could also state, and I'm not going to write this for all of them, but I could also state this in the reverse, and it would be exactly the same statement. That if I have log b of xy, that's equal to log base b of x plus log base b of y, right? So what that means is you can put them together if you need, or you can take them apart if you need. It's kind of like factoring. You can either distribute or you could factor it out. It depends on which one you need. Okay, so that's the first rule. Now I'm going to go ahead and prove this rule. So here's our proof. So we're going to start with these two quantities, and I'm just going to assign them a value, right? I'm not picking a number, I'm picking a letter to assign the value. It just makes the proof a little easier. So we're going to say log base b of x, and I'm just going to call that m for the moment. And then we have log base b of y, and I'm going to call that capital N. Okay, so if we have these two quantities, we can rewrite these in exponential form, which means that b to the m is equal to x, and over here b to the n is equal to y. So all I've used is the definition. Right, that's just satisfying the definition of a log. Well, if this is actually equal to this, then if I multiply them over here, so if I multiply the bn times this, so we'll go times b to the n, and then on this side, it'll be times y, right? Because b to the n is equal to y, we are still multiplying both sides of this equation by the same value, right? So that's a legal move, which means that b to the m times b to the n is equal to x times y, right? And here's where the magic happens, because we're using rules of exponents. If since I have like bases here, this is now b to the m plus n is equal to xy. Well, I'm going to do this. I'm going to jump it over here. If we rewrite this one in logarithmic form, right, that would be log base b of xy is equal to m plus n. Okay, well, look at what m and n are, right? I have log base b of x and log base b of y. So if I just substitute that back in, what I end up with is that log base b of xy is equal to log base b of x plus log base b of y. I did notice that I'm capitalizing certain logs and not capitalizing others. That actually has no bearing on the logarithm at all. I think I'm doing it just because I feel like I should capitalize the first letter of a sentence for whatever reason. So, but this is how the proof proceeds. We start by assigning a value to each logarithm. We rewrite it in exponential form, and then we use rules of exponents basically to combine those two equations and then change it back into a logarithm. And we can see the property. The only thing that's important here is the final product. I mean, it is important how we got to it, but the final product is what we're going to be using here, right? And you'll notice that matches with this one completely, right? Those are the same rule. They're just written in opposite directions. Okay. Well, I wonder. How far we have to go here. I don't know why I'm doing it this way. Okay, so we have our first rule. Now, the second rule is the subtraction rule. Actually, no, let's do the power rule first. Because the subtraction rule is a consequence of the addition rule and the power rule. Or power property. Okay, so we need to show that the power rule is true. And the power rule basically says that if I have a log base b of x to some power, what I can do is bring that power out to the front and multiply it by the log. And then leave the argument without an exponent. So you notice what happened is the exponent basically moved to the front. It just dropped down to the front. This is actually the property that's going to be our key to solving most equations, because once you have a log in there, you can pull the variable out of the exponent if it's an exponential function, and that's what you need to do to solve. You need to get the variable out of the exponent place. So that's actually where that's going to get used. But let's look at why it's true. So first of all, I want to point out, and it's probably easier to see if I just use a number instead of n. So let's say I have, not log. There we go. Log base b of x to the third, right? Well, the addition rule says that I can split this up to log base b of x plus log base b of x plus, oh, I ran out of room. Log base b of it. Try that again. Hopefully you have the idea there. We'll see if I can do this or not. Plus log base b of x. So it shows up 3 times, one for each x, because that's an x times x times x, right? So that's the multiplication. The addition rule says you can break it up this way, but it's 3 of the same value. So that ends up being 3 times log base b of x. And notice the exponent came down to the front to become this. So you don't need to write this every single time. You can just bring the exponent to the front. Okay, so that's our second rule. Now the third one that we're going to use, and it looks like I'm going to be able to keep all these rules on the same palette, so that's good, is the subtraction rule. And the subtraction rule really gets used as a combination of the power rule and the addition rule. So subtraction property, oops, that didn't change my color. Now, I want to point some things out here. Because if you think about the rules of exponents, just exponents, not logs. Rules of exponents say when you multiply like bases, you add the exponent. So here we can see a manifestation of that. I'm multiplying things, it turns into addition, right? Same way when we multiply like bases, we add the exponents. In fact, we saw that in the proof. We had to add exponents to get this property. The power property also relates to that. When you raise an exponent to a higher power, you multiply the two exponents. The subtraction property shouldn't be too much of a surprise because it talks about what happens when you divide two. If you have a subtraction, it turns into division. And if you think about what you do with exponents, when you divide like bases, you subtract the exponents. And so we get a very similar property here that says that log base b of x minus log base b of y is equal to log base b of x over y. Okay, so that's the subtraction property. And it basically works like this, right? If I have log base b of x over y, right? We can prove this in the reverse order. This is the same thing as log base b of x times y to the negative 1, right? Remember, negative 1 means to divide, right? Well, now we can use the addition rule to split this up. Log base b of x plus log base b of y to the negative 1. And now we have the power rule. I can take this negative 1 and drop it out front, and that gives me log base b of x minus log base b of y, right? So that means that the log of x over y is equal to the difference of the two logs of the numerator and denominator, right? So these are the three properties. And by themselves, they actually seem a little confusing. And if you were using them one at a time, it would actually, it would make things a little bit clunky to use them one at a time. So let's see how these things are used now. We'll see, when you use them, it actually becomes pretty fluid because you can do multiple rules at the same time to take care of things. So let's go ahead and start here. So let's say, let's try that again. And I'll switch colors so we can look at problems in a different color than the properties. So let's say I want to expand as much as possible I know that's a very vague command. But let's say we're starting with this. So let's say we have log base 2 of 2x over y, right? We'll keep the argument of the log. By the way, the thing you shove inside of a logarithm is called the argument. We'll keep the argument of the log fairly simple to start out with. So what you want to be thinking is what rule applies first off. And I can see the division rule applies. So I'm going to start there. So that means that I can break this up into log base 2 of 2x minus log base 2 of y, right? Well, we're not completely done because I still have a product over here. So that means I have log base 2 of 2 plus log base 2 of x minus log base 2 of y. Okay, now, under normal circumstances, we'd be done, but there's one log that has a number shoved into it. And if it's easy to compute, you should actually compute it. I'm not talking about being able to plug it into your calculator. I'm talking about just using normal properties of logs. Can you get that to be just an integer or an easy to read fraction? And you think about it, 2 to what power is 2? And the answer is 1, right? If the base matches the argument of the exponent, the answer is 1, or the argument of the log, then the answer is 1. So this is 1 plus log 2 of x minus log 2 of y. Now, I'm going to point some things out that'll shorten your work on the next one. Right, the numerator has two factors. Right, in fact, I'm going to do it this way just so we can see how this goes a little bit quicker. I know I'm going to have a log for each one of those factors in the numerator. Anything in the numerator, those terms remain positive. So just looking at that, I know I can immediately jump to log base 2 of the first factor of the numerator, which is 2. It's going to be plus, anything in the numerator is a positive term, log base 2 of x. And then I've used up the numerator, so now I turn to the denominator. Any of the terms that you get from a denominator are going to be negative terms, just like this one is, right? So that's in the denominator, so I know it's going to be a minus log base 2 of y. And now I just look through to see if there's any logs I can simplify, right, and actually compute. And I found this one, so that's 1 plus log base 2 of x minus log base 2 of y. Right? So the next one, I'm actually going to use the shortcuts to compute, because that's how I'd rather have you doing it in the long run. I think it's a good exercise to see if you can do it computing one step at a time. That's just to give you a feel for it. You really want to be computing these as many at the same time as you can. Okay, so let's look at another one and see if we can make this go a little bit quicker. Okay, so let's say we're trying to expand this. We have the natural log of, actually, I'm going to make this one a little nicer here to start out with. X squared y over z, right? We'll just start it there. In fact, let me put some exponents on here too. So I'm going to make this z to the 4th, and I'll make this y to the 5th. Okay, so I'm going to show you the quick way of doing this, because you can kind of, like I said, you can use most of these rules simultaneously. So the first thing I want to point out is that I'm going to be pulling out an ln x. So natural log of x, it would be squared. But remember, what we can do with exponents is they get pulled to the front. So I can do all of that at the same time. I know the term's positive because it's in the numerator, and it's going to have a coefficient of 2 because it has an exponent of 2. So I'm writing the exponent as a coefficient and taking the natural log of that factor. Then the next one is going to be plus 5 times the natural log of y. And then in the denominator, right, and remember, this would be z to the negative 4th, right? So it has minus 4 as a coefficient. It's in the denominator, so it's minus 4 times the natural log of z. And you can see we spread it out pretty quickly, right? I don't have any of the steps that I wrote down before. I handled each term one at a time. So exponents become coefficients. If it's in the numerator, it's a positive term. If it's in the denominator, it's a negative term, right? If you remember those things, these things go pretty quickly. Okay, so let's look at the next one here. Okay, let's look at this. Let's say we have log base 6 of x times the square root of y over the cube root of z. Okay, now, before you have a heart attack on this one because of the roots and stuff, remember that roots can be written as exponents, and we have a property that tells us what to do with exponents. So if we just change the form of this, we can see how this works out. Okay, so let's do the same thing we just did. So log base 6 of x, and I have an exponent of 1 on x, so I'm not going to worry about the coefficients because it's just a 1. Now, the next term, if you don't see it right away, then just write it down with the root on it. So that'd be log base 6 of the square root of y. And then it would be minus log base 6 of the cube root of z. Okay, now, remember, like I just said, these roots are exponents. We could have rewritten them up here, but I'm going to rewrite them in this spot. So this is now log base 6 of x plus log base 6 of y to the 1/2 power, right? Because a 1/2 power is a square root. And it would be minus log base 6 of z to the 1/3 power. So now I just need to pull these exponents out to the front. So log base 6 of x plus 1/2 log base 6 of y minus 1/3 log base 6 of z. Right, it's getting a little cramped there at the end. Sorry about that. But yeah, it's, and if you can see that the root is a 1/2 power, you can actually jump straight to the answer on that too. It's the coefficient is always 1 over the index of the root. And one of the things that's never written is that, well, maybe I should write that in a different color. Square roots have an index of 2. It's just never written, right? Because if you leave it off, it's just understood to be a 2. Okay, so let's ramp it up a little bit more, right? And see what we got out of it. See what else we can get out of this. Let's do that. Okay, so let's have a lot of fun with this one. So let's look at the log of x cubed times the square root of x squared plus 12. Ooh, it's getting crazy already, isn't it? And that's over x minus 4 squared. Okay, so this one's a little bit more of a challenge. I want you to pause your video here and see if you can work this out, right? And then we'll work it out together. Okay, I'm assuming you have paused it at this point. So some things I want to point out. First of all, the base of this log isn't written, right? And if it's not written, it is understood to be a base 10, right? So we just need to understand that that's a 10. You don't have to write the 10. Now, let's go ahead and rewrite this argument so that everything is exponents. I could have done this with the last one as well. So it's x to the third times x squared plus 12 to the 1/2 power over x minus 4 squared. Okay, so now that we have it rewritten, let's go ahead and tear it apart. So in my numerator, I know I'm going to have 3 times log x, right? That's from the x cubed. The next term, now if this was x squared times 12, we'd have a couple of terms here, right? But we have no way of breaking up an addition inside of a logarithm. So what the second term ends up being is 1/2 of, oh, hang on a second. I don't want the parentheses yet. 1/2 of the log of x squared plus 12, right? Don't get confused and break that up into 2 terms. You can't. These aren't factors, right? They're being added together, not multiplied together. And it only works if they're being multiplied. And I should have left myself just a hair more room. Let me see if I can, let's see if I can grab this and move it. Let's try that again. One more time. Maybe if I try it on this side. Well, let's just do this. Okay. Well, I moved part of it anyhow. And then the last term is that denominator, the x squared, the x minus 4 squared. So that's going to be minus, because it's in a denominator, log, minus 2, sorry. And then the log of x minus 4. Make sure you put parentheses around if you have a sum or a difference inside the log, make sure you put parentheses around those, because otherwise it looks like you're adding 12 to the log of x squared or something like that. And that's not what you do. And this exponent also can't be moved because it's locked up in a sum, right? It would have to be the exponent of an entire factor, not just one of the add-ins in a sum. Okay, so this would actually be the way to break this one apart. All right, so let's look at the next one here. Let's see here. There we go. Okay, our next example, we're going to go in the reverse order. So instead of expanding, you're going to be asked to condense. Condense the expression as much as possible. This oftentimes you're asked to just write something as a single logarithm, right? Because that's really your goal. It says condense as much as possible, but the goal is to write it as one. You have this list of logarithms and you want to condense it down so it's one logarithm. So let's go ahead and take a look at some of that. So let's go ahead and section that off again. So let's say this is the expression I'm starting with. Let's say I have log x. So this is the common log, the log base 10, minus 1/6 y plus 2 log z. There we go. Okay, so let's just go ahead and look at how to put this back together. We want to write this as a single log. So you can skip over a lot of the condensing steps just by knowing where the pieces are going to go. So first of all, I have both positive and negative terms, which means I get numerators and denominators. Anything that's a negative term goes in the bottom. So I know I have a fraction in here. Let's do the numerator first. So we'll just collect all of the positive terms and write them in. So log of x, the coefficient's a 1, so that means it's just a plain x here. Okay. Oh, I'm sorry, that was supposed to be a log. Log 1, having issues here. That's supposed to be a 1/6 log y. Let's do that. I wrote the wrong, I missed the log in there. Sorry about that. Okay, now the other positive term is 2 log z, which means that this 2 is going to be on the z, which makes it a z squared. Right, so far so good? Good. Okay, the last thing now is I have that negative term. And the 1/6 is going to go up and become an exponent of y. But y to the 1/6 is the 6th root of y. So this is actually log x z squared over the 6th root of y. Right? And if once you get fluid with that fractional exponent like that, you can even jump straight to the answer on these as well. Right? So it's just a matter of pushing everything back together to undoing everything you just did. So if you understand how it came apart, you'll understand how to put it back together. Okay, so let's look at another one here. Okay, so let's do that, and then back to that. There we go. Okay, so I want to give you a couple to play with. These are for you. So let's go ahead and start with 2 log base b of x plus 5 log base b of y. Okay, and then we're going to also look at the natural log of x minus 1/2 the natural log of 7. Okay, so pause this here and see what you can do with these two to put them together. And then we'll look at another one right after that and see what we can do with that one. Okay, so pause it here. Okay, I'm assuming you've paused at this point. So here we have, let's see, if we're going to, not log. We know it's log base b. I don't have any negative terms, so I don't have a fraction. So we just need to put these things together. This would be x squared, right? And then over here, this would be y to the 5th. And that's our final answer. I actually meant to do that in a different color so it'd stand out a little more. But yeah, that's our answer. It's really that straightforward. Just put the exponent where it goes. Anything that's being added, you turn into multiplication in the numerator. Anything subtracted goes into the denominator. Okay, so now let's look at this other one here. Okay, so we have the natural log So that means we're going to be dealing with the natural log. I have both positive and negative terms, which means I have a fraction. The natural log of x is a positive term, which means x goes in the numerator. And then down here, this is my negative term, so it goes in the denominator. And I know there's going to be a 7, and I'm going to be raising it to the 1/2 power, which means that it's a square root of 7. Okay, now I do want to point out something here. One, I know probably many of you have had it hammered into your head that you have to rationalize the denominator, right? You're not allowed to have square roots in the denominator. There used to be a good reason for that, and it was because it was very, very difficult to compute a decimal approximation by hand if there was a square root in the denominator. There are other reasons to do it as well, usually having to do with computational things. But when it comes to just numbers and stuff like that, it's actually just fine to leave the square root in the denominator because you have a calculator, right? You can get a decimal approximation pretty quickly if you want to. So it's actually not, it's not against the law. It's just kind of what people don't do anymore, right? So in any case, this is a perfectly fine answer. Although if you did want to rationalize the denominator, it would look like this. It would be x root 7 over 7, right? If you did go take it that far. Those are both completely correct answers. And if you're wondering how I did that, I just multiplied top and bottom by root 7, right? It just changed the fraction. Okay, so good. Hopefully you got through those without too much issue. So let's look at another set real quick. Oops, wrong one. Let's do that. And we'll go ahead and delete that. And yeah, let's try one that might give you a little more issues, but I want you to try this one because by this point, you should be able to start manipulating these things using things you already know. In fact, let's put it in Poiple. Okay, so we'll go 1/2 times log base 5 of x plus log base 5 of y minus 2 log base 5 of x plus 1. Okay, now these are about as complicated as they get on here. So let's see what you can do. Let's see if you can piece it together on your own. It might take a little while to, if you're still trying to get your bearings here, but take a few minutes and see if you can come up with a single logarithm that describes this expression. And then we'll take a look at it together. All right, I'm assuming you've paused it at this point. So let's go ahead and play. So first of all, I can join these two logs together as 1/2 times 1/2 times log base 5 of xy. Right? I can do that directly, which means, well, yeah, I'm just going to leave it there for a second. I can do this. Log base 5 of xy to the 1/2. Right? And you have to make sure you put parentheses on there because otherwise that means it only applies to the y. If you want it to apply to both, you have to put parentheses. Now, the second term here, we can simplify a bit. I can move the square over here, so this is now minus log base 5 x plus 1 squared, right? And now we can start, we can use that, the subtraction property, and I can turn this into division. This is now log base 5 of, well, I'm going to go ahead and turn this into a square root of xy over x plus 1 squared, right? It condenses pretty quickly. And it's just a matter of knowing where all the pieces need to go, right? Once you do a handful of these, you actually get pretty quick at it. So make sure you're practicing up. And, of course, if you have questions, please ask them. Now, there's one more thing we need to hit. And this is actually, some calculators will handle things like a log base 5, like I think some of the Casio calculators do it. But let me go ahead and erase this. The vast majority of calculators have only the natural log or the common log as a button. So how do you deal with things like that? And what we do is we use the change of base formula. So I'm going to write it down first, and then I'll show you why it works. It actually works because of all the properties we just found. So here's the change of base formula. If you have a log, base b of some value x, right, and you want to switch it to some other base. So this is basically going from base b to base a. This is equal to log base a of x divided by log base a of b. Okay, so before we actually see how that works, I'm going to show you why it works. Okay, so first of all, let's say I have log base b of x, right? Well, if those are numbers, if b and x are numbers, then that has to be equal to something. So I'm just going to say it's equal to y at the moment. Okay, now if I rewrite this using properties of logarithms, right? The definition of logarithm, actually, that b to the y equals x. Okay, so we have another equation now, and I can take the log of both sides of this. So that's what I'm going to do. But I'm going to use log base a this time. Right, so we have log base a. So now it looks like this. Switch back. Come on, fingers. Log base a of b to the y is equal to, is equal to log base a of x. Okay, well, this is where that solving property comes in. Y is an exponent, which means that I can take that y and I can put it out front, right? Which means that I have y times log base a of b is equal to log base a of x. Well, log base a of b is a number, which means I can divide by it. And you notice that's the right-hand side of this thing. These guys cancel, and I end up with y is equal to log base a of x over log base a of b. And so now we've just converted it to log base a. Now typically a is either going to be e, right? So that makes it a natural log, or it's going to be 10, which makes it a common log. And those are the things that you can plug into your calculator. So, and just to show why this statement makes this true, we took log base b of x and said it was equal to y to start out with. We did a bunch of manipulation and we found out that y is also equal to this value, which means that this value and this value have to be equal, right? These guys are equal. That's the biggest sideways smiley face ever. But yeah, those two things are equal because they are both equal to y. And so putting them together gives you this formula. Now, all we really have to do at this point is use it. So I'm going to go through a quick example of how to use it. It's actually not too difficult. It's just plugging it into the calculator and knowing what to put where. Okay, so I'm going to reorganize real quick. All right, so we got the calculator set up here. Now, when it comes to this formula, one of the things that people run into problems with is remembering it, right? One of the ways I remember how to use this formula is, and the thing that confused me was, which is x in the numerator or is x in the denominator, or is b in the numerator, b in the denominator? I always had problems keeping it straight which one was which. So the fact that the formula uses b is actually useful. What I always think about it this way: b is the base on bottom, right? Bottom starts with b, so it goes in the denominator, it goes on the bottom. If that helps, great. However you need to remember it is fine. You just have to remember it. Okay, so let's take a look. Let's say I want to work out something like, in fact, let's pick something we know the answers to so that we can check to make sure the formula is working right. So let's say we're looking at log base 5 of something like 25, right? Log base 5 of 25 is 2, right? Because 5 squared is 25. So what we want to do here to verify that we know we're using the formula correctly is we want to try to plug log base 5 of 25 into our calculator using this change of base formula and see if we can get 2 out of it. So let's try. Now we have 2 bases we can pick from. There's one base on your calculator. Let's see, where are they? Yeah, you'll see one of them. It just says log. Oh, actually, that's a capital O, right? One of them says log, and that is log base 10. That's your common log. The other one is the natural log, and the natural log is log base E, right? So that's just a reminder of what those things mean. So A is either going to be 10 or it's going to be E. And it doesn't matter which one you pick as long as you use the same one through the entire formula. So let's try this. Let's actually do it with both. So let's use the common log first. So we want, let's see, x is the argument, so that would be log 25 divided by log 5. Okay, so we want to enter that in the calculator. So we want to hit log, right? So I hit the log button. Let's see, 25. And then remember to close your parentheses, otherwise it'll include the fraction inside the logarithm. So we want to close that and then divide by log, and it's base 5 we have written here, or the log of 5 we have written here. So we'll go ahead and enter, and we should get 2. Hey, we did, right? And by the way, log 25 is not a nice quantity. I mean, let's just look at what that looks like. This is an irrational number because it's base 10. It's asking 10 to what power is 25, right? And that's just where the decimal stops. It goes on forever. Same thing with the log of 5, right? If I look at log 5, that's also an irrational number, but when I happen to divide them, I get 2. I think I actually find that quite fascinating, to be honest with you. So yeah, so it worked here, right? We got 2. So let's just make sure this works across the board. Let's try the same thing with the natural log. Now, you're going to get 2 different numbers for these, right? If the natural log is the one that says ln, and that's right underneath the regular log. So I just want to point out before I do the full computation, the natural log of 25 is also an irrational number, but it's not the same number as the last time, right? The log of 25 is 1.397 dot, 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 dot. The natural log of 25 is 3.2188 dot, 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 keep going with that. So these are actually vastly different numbers, but we still get the same answer at the end. Okay, so let's take a look at that. So we get the natural log of 25. We want to divide that by the natural log of 5. As long as you're using the same logs in the quotient, you should be fine. Yeah, we got 2 again. So we've gotten 2 every way we compute this. Right? Now that's something we already know the answer to. But oftentimes we get kind of crazy things in here. Right? I could end up with something like log base 6 of 17 or something like that. Again, it's not going to matter which log you use as long as you plug it into the formula correctly. I can do natural log of 17 over natural log of 6 and see what I get. All right, so let's see. And then I'll show you how to check your answer on these. Okay, so we got, and you could use the regular log also. So the natural log of 17 divided by the natural log of 6 should be something irrational, and it is, right? So we get an estimate. In your homework, it'll tell you where to round. right? So that goes on forever. Here's how you check your answer, right? If this is actually a true statement, log base 6 of 17 is equal to 1.5812, dot, 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 then that means that 6 to this power should be 17. Now this was rounded, right? So it's not going to be exact, but it should be really, really close. So let's do that. We'll go 6 to the, and then 1.58. And you could either plug it in or you could use second function and pull the answer up if you want. But 1.581246, that's probably far enough. And we'll just hit enter, and we should get something very close to 17. And we do. So that means that our estimate is a good estimate, right? But that's how you check your answer. You take the answer and you use it as an exponent on the original base and see if you get the argument back. Okay, so those are the main things I wanted to get through today. I wanted to get through the properties of logs, how to tear a log apart into smaller pieces that each term contains a log, or to take a big expression and condense it down to a single log, or to convert from one log to another so you can use your calculator on it. And those are the three things I wanted to get through, and I think we just got through those. So until next time, and by the way, next time is going to include solving equations with logs and exponents. Until next time, keep your pencils and your wits sharp.